You've probably heard of the terms like complement of a set and something similar to that. Well, that falls under set operations. It's something that you've touched on during your days in secondary and primary school. So we just have a brief introduction of that before we proceed to solve our question. So this will be the first part of the video, and we did the introduction to set theory. And if you haven't watched the video, I'll drop the link in the description. Both part 1 and part 2. I think there were two videos on set theory. So now we are looking at set operations. So you've probably seen something like this. Yeah, where this thing here on top would denote a complement of a set. Sometimes the complement of a set will be written with a small c on top there. The two mean the same, so they can use either of the two to denote complement of the set. So now under set operations, the first thing that we'll look at is complement of the set. We'll want to understand what complement of a set is. So how can we define a complement of a set? How can we define it? Well, for the start, we know that all the sets that we do with, they are defined. Yeah? They are defined by the universal set. So your universal set is a set that will contain all the elements. All the elements will come from the universal set. Now, so a complement of a set, which is denoted by either of these, either with a c on top or the other one. So a complement of a set, we'll say set A in this case, a complement of a set A, which can be denoted of this with respect to the given universal set, and usually the universal set will be denoted by the letter U, which represents the universal set. So is a set of all the elements or members of the universal set that do not belong to A, right? So this can be defined or given as a set builder notation. For example, if we talk of a set A and we want to define it in terms of the universal set, we can write this complement of a set A. So we can use like a small c on top or this mark here. So we want to define this the set builder notation. So say we're talking about the element of x, so element of A, so we can say that element of A will be represented by x. So say x is such that x is a member of the universal set, right? But those elements are not part of A or do not belong to the set A. So whatever elements that are in the universal set but are not part of A, then it means we're talking about a complement of a set A. So basically, to just try break down these things, what we're saying is that if you look at a list of the elements in the universal set, then you look at a list of elements in a set A. So those elements that are in the universal set U but are not in the set A will make up a complement of A. Okay, let's try to look at an example for us to understand easily. I think we can have an example here. All right, look at this example. It says U, which denotes the universal set, is given here. So I have a list of members of set U, and A, we've also been given A. Perfect. So now the question says list down the elements of A. Well, when you look at this universal set here, you've got 1, 2 up to 10 as the elements of the universal set, meaning A, whatever is in A should come from this, should be confined within this. So we are being given set A. So you notice that the elements in set A are also in the universal set. But we're told to find the complement of the universal set, meaning we'll look at the members that are in this set, the universal set, but are not part of A. So here we have set A, these members here. So we will exclude this. Whatever is going to remain when we subtract this element from here will make up the complement of a set A. So in this case, our complement will be 2, 4, 6, 8, and 10. Right? So that will make up our complement of the set A. I think this puts us somewhere. Right, so this is the complement of a set A. So we just want to familiarize ourselves with the terms that are used. So we now understand what a complement of a set is. Let's try to move and see how we can define union of sets. So the term union simply brings the aspect of bonding or bringing together, unifying, adding, something like that. So union of sets, it means you are getting those sets and putting them together, then you have got a union of the set. So a basic definition, you can say the union of two sets, let's say those sets are A and B, will be denoted by, there's a symbol that is used, right? Yeah, so since it's union, we usually use this, the U symbol. This would denote union of the set. Yeah, union of the set is usually denoted by this. So if we talk of the union of set A and B to be A union B, yeah, this is what I'm talking about, A union B. So the union of two sets A and B is denoted by this. So now that union is the set of all elements that belong to A or B or both. Not to complicate things, eh? So maybe an example will help us understand so that we shouldn't get confused. So if we say, okay, we'll first try to write this in a set Juda notation just to have the basic understanding of these things. So we are talking of the union of set A and B. So we'll say A union B as a set Juda notation. So the elements of this set will be X is such that X is a member of A or X is a member of B. So notice this term which I'm using. Oh, it's a very important term that you need when you're dealing with sets. It's a set language. Set operations has its own language. So these are the language. These are the words that you need to understand when and where to use them. So note that the definition can be extended to more than two sets. We can have three sets. So let's look at an example where we can have a union of the sets. Yeah, here it is. So we'll let A be that. Okay, we're given A 2, 3, 4. B also be that. Then we're told to find A union B. So what you do here, we've got our set A and our set B. The union means we're getting these two sets and putting them together. So the union will comprise of 2, 3, 4, 5, and 6. Notice that we've got 4 in here and 4 in here. Why don't you write 2, 3, 4, 4, 5, and 6? Well, that is wrong. Since we're talking about the union of the set, it means we want to find the elements that are in both sets. Something like that. So the elements can be in here or in both. Back to the definition. So we'll just represent 4 once. So we have 2, 3, 4, 5, and 6. So that will make up the union of set A union B. Then we can move to the intersection of sets, right? So here's the definition. The intersection of two sets A and B denoted by A intersection B. So this is the sign or the symbol that is used when we're dealing with intersection. So is the set of all elements that belong to both A and B. So we've got two sets. Now they've used the term both, meaning the elements that are represented in the intersection of the set should be in all the two sets. If we've got set A and set B, meaning the elements that we find in set A and the elements that we find in set B, if they are the same, then they'll make up the intersection. So it has been defined or represented as a set Juda notation here as an example, X such that X is a member of A and you notice the difference between intersection and union. There we had O, meaning even if in the other set it's not there, it will still be represented. That was the case here. We had 5 and 6, which isn't part of A, but it was represented same as 2. But in this case, it requires us to have all the elements in the two sets. And so it's another term that is used in set theory or set operation as a language. So I'm hoping of an example. Okay, so note as well here that the definition can be extended to more than two sets. So you can have multiple sets, then you can find intersection. You can have as many as 10 or more than that. so you can find the intersection. So in the future videos we'll see how we can apply this concept in real life, right? So I believe we've got future ministers here. Now, if or n two sets A and B, A intersection B equals empty. I'll read that again. If for any two sets, so we're talking about set A and B, then if A intersection B is empty, then A and B are said to be disjoint. So what they mean here is, let me put this graphically here. So if we've got a set A, I'll use something like a Venn diagram like this. So we can have elements, let's say 2, 3, and 4. Then here we can have 5, 6, 7. We don't have anything that's common in these two sets, meaning they are disjoint. There's nothing that intersects these two sets. So the intersection of this set will be empty. So this will be a disjoint set. If you are to list here, A will be is going to have these elements, and B is going to have these elements. Nothing here is common. That's what they basically mean with this term when they say that it will be a disjoint set. So another example here is let's say A, B, 2, 3, 4, exactly what I used, and 4, 5, 6, find A intersection B. So you see here that the only term or number that's common is 4. It's the one which unifies or intersects these two sets. So our A intersection B is going to have one element, which is 4. So these terms which have been repeated and or are the terms which we need to familiarize ourselves with. Alright, so if A and B are sets, okay, we write A minus B read as A minus B to mean the set of all elements which belong to A but do not belong to B. Okay, so before we look at this Juda notation, I want for us to understand this, basically let's look at this. So what they mean, A minus B is the same as A intersection B complement. I think this will make a lot of sense when we start to deal with the Venn diagrams. So we're saying from set A we're subtracting B. That's A minus B. We don't want the elements that are in B. We just want A minus those elements that are in B. So that thing can be interpreted as A intersection B complement. Why? Because we don't want what is in B, and what is not in B is the complement. So we get these two sets that will make A intersection B complement. It has also been defined as a set Juda notation to say X is such that X is a member of A, but and X is not a member of B. That will give you A intersection B complement, or A minus B, because we've removed the elements that are in B, right? So the last example here before we move to Venn diagrams and also peruse through is this one. So we're told to say let U be the universal set. In fact, in most of the questions they won't even mention to say U is the universal set, but basically when you see U, they would usually denote the universal set. So just let it pop that it's the universal set. So let U be this 1 up to 10, all positive is are the members of the universal set. So we've been given A to be that, B to be that. These are elements of A intersection B, or A minus B. Well, we'll look at A. These are the elements that are in A. We've been given 2, 3, and 4 in B. So we're going to remove whatever is in B from the set A. So in this case, we only have 4. We only have 4 that is in both sets. Now we don't want this 4. We want where A intersects the complement of B. What's the complement of B? The complement of B are the elements that are not in set B. You get, right? That are not in set B. And it gets us back to the Venn diagram. B complement will consist of the sets. We just, from this Venn diagram, we just subtract 4, 5, and 6. Whatever remains in the Venn diagram. Then where it intersects with A. So we have 2 there, you also have 3. This will make up A intersection B complement, or A minus B. So in this video we'll end here, then we'll continue with Venn diagrams and other set operations or operations on set before we move on to solve a lot of questions on this topic. So again, this was a viewer requested video from a student. Actually 2 requested for this. We have one from Unilas and another one from Unza. So remember to subscribe and hit the notification button, and please, you can drop all your questions in the comment section, then I can do up a video from there. And the greeting from this video will go to Rajesh from Bangladesh. Yes, Rajesh was our new subscriber who made the rapid progress and has been helped with these videos. Thank you very much, and God bless.